So, have you ever just stopped and wondered how a machine, a thing that only understands pure logic and numbers, can somehow get the poetry, the sarcasm, and the meaning in our language? Well, today we're going to pull back that curtain. We are diving into how AI actually learns to read, breaking down the very first and honestly the most critical steps that turn our words into ideas a machine can understand. All right, here's our game plan for today. First, we'll look at how machines fundamentally see text in the first place. Then, we'll get into the two key ingredients, tokenization and word embeddings. After that, we're going to explore the amazing word math that this whole process unlocks. And finally, we'll wrap it all up and see why this is the foundation for pretty much all the AI you hear about today. And this really is the fundamental problem, right? We think in ideas, in feelings, in context. A computer, it thinks in ones and zeros. It has no idea what a dog is or what loudly even implies. So how on earth do you bridge that gap? How do you translate our rich, complicated, messy language into cold, hard mathematics? Well, the answer is we don't really teach the machine our language. Instead, we translate our language into its language. For an AI to do anything useful with text, whether it's summarizing an article or answering a question, it has to convert that text into a format it can actually work with: numbers. I mean, you can't just feed a whole novel into a computer and expect it to just get it. The very first thing you have to do is chop our sentences down into smaller, manageable, standardized little pieces that the model can process one by one. And this whole chopping process has a special name. It's called tokenization. You can think of it as the essential prep work in the kitchen. Is what has to happen before any of the real cooking, or in this case, learning, can even begin. So what is tokenization, really? It's just the process of splitting text into these small units we call tokens. The best analogy is a chef dicing an onion. You take a whole complex thing, a sentence, and you chop it into consistent, predictable pieces. A token can be a whole word like run, a part of a word like ing, or even just a piece of punctuation like a comma. This image gives us a perfect peek into the machine's point of view. It doesn't read the phrase think step by step. No, it sees a sequence of separate colorful blocks, the token for think, then step, then by, then another step. Each one is its own distinct piece. This is literally the beginning of how a machine learns to read. But, it's not as simple as just splitting at the spaces between words. As you can see here, there's a really important trade-off. Do you use smaller tokens, like individual letters, or bigger ones, like whole words? If you go small, the model gets really good at handling typos and new words it's never seen. But it takes a ton of processing power. If you go big, it's way faster, but the model can get totally confused if it runs into a word that wasn't in its dictionary. Okay, so once we have all our tokens, the next step is actually pretty straightforward. The model basically has a giant dictionary, and it looks up each token and gives it a unique ID number. It does this for every single token until an entire sentence becomes just a long string of numbers, exactly like the example you see here. We have officially turned our words into integers. But this brings up a huge question. The number for dog, say 452, and the number for cat, say 817, they're just random labels. They don't tell the model that dogs and cats are both animals, that they're both pets, or anything about their relationship. These numbers have zero built-in meaning. So how do we fix that? And that leads us to the second, and frankly, much more magical step: word embeddings. This is where we stop just labeling words and start actually understanding what they mean and how they connect to everything else. The best way to get this is to use an analogy. I want you to picture a giant, complex, multi-dimensional map. And on this map, every single word you can think of has a specific location, a specific point. And its location isn't random. It's determined entirely by its meaning. So a word embedding isn't just one number. It's a long list of numbers, a vector. You can think of this list of numbers as a set of coordinates, like GPS coordinates, that pinpoints a word's exact location on that giant meaning map. The model learns these coordinates by analyzing billions of sentences, slowly figuring out that words that show up in similar contexts should be placed near each other on the map. And this is what that map of meaning actually looks like in practice. The AI, just by reading massive amounts of text, learns to group similar ideas together. So all the fruits, like apple and orange, they all end up in the same neighborhood on the map. Over in another area, you'll find all the cities like Berlin and Tokyo. The model builds this entire map of meaning all on its own. Now, having this map of meaning leads to something that is just incredible. Once our words are basically coordinates or vectors, we can start doing math with them. And this isn't just regular math, it's more like a form of reasoning. The idea is pretty simple when you think about it. If words are just points in space, we should be able to add and subtract their coordinates, right? And by doing that, we can actually navigate the map and explore the relationships the model has learned. This brings us to probably the most famous example in all of artificial intelligence. What do you think happens if we take the coordinates for the word king, subtract the coordinates for man, and then add the coordinates for woman? Just think about what we're doing here. We're starting at the concept of king, then taking away the concept of man, and adding the concept of woman. Where do we land? The resulting vector lands almost exactly on top of the vector for queen. I mean, come on, that is the big aha moment. The model didn't just memorize definitions, it learned the abstract relationships between concepts like royalty and gender, and it managed to encode that relationship mathematically. And here's the most important part. This isn't a one-off party trick. This works for thousands of different relationships. The model learns from the data. It figures out that Paris is to France what Berlin is to Germany. It learns grammar, like plurals. It even learns opposites. All of this deep semantic knowledge gets baked right into the geometry of this word map. So that brings us to the big finale. Why does any of this matter? It matters because this whole process, turning words into meaningful numbers, it's not just some clever programming trick. It is the absolute bedrock of all modern AI. This diagram shows you exactly where everything we just talked about fits in. If you've ever used a tool like ChatGPT, you're using what's called a transformer model. And look, right there, at the very beginning of the whole process, input and coding. That's it. That's tokenization and embeddings. It is the front door that all language has to walk through before anything else can happen. Literally every amazing thing a large language model can do, from answering your questions to summarizing a dense article to writing actual computer code, it's all built on this fundamental ability to turn our language into these rich, meaningful vectors. Without tokens and embeddings, there is no AI as we know it today. Simple as that. And that leaves us with one final, pretty big thought. We've just seen that machines can create a mathematical map of human language, capturing all of its complex relationships. So the real question is, what's next? What other complex human concepts, things like emotion or logic, or maybe even creativity, are they learning to map out right now?